confused as to how I'm supposed to like have that equation in my team.
Can you email me the link so that I can have some on my side?
Yeah. One less.
No, I should
He's finished 24. Did you take it? I know, we had this conversation already, because I saw it, she's in my, that's okay. Do I try? I know what it is, but I don't want to. It doesn't sound very, it sounds like weird. Actually, I don't know. Trying to.
Okay, you're not.
Yeah, I think that's. Well, for what? That's like so. Sorry, yeah, I guess.
I'm sure everyone.
No, like, it's just. No, it's not, I wouldn't really tell why. Yeah, that's so just. Probably not this time.
You're Midwestern.
You know.
Like,
Yeah, I do that.
oh, it's like.
It just started in that way for your class. Like what episode of the
Of course you were.
Yeah.
I mean, that is getting in like.
It's like a.
I don't know, it's just like not universe.
Then I just have like a weird.
Oh, I'm not even thinking about the next. I thought you were thinking about. Wait, this summit, is this? Oh, no, it's not. Yeah, it would be like. It would be added.
Yeah, they'll be like, oh.
I don't really know. I know that you're gonna.
Is that your account? Actually, you're the one who's writing down.
Took like Chinese class for like 6 years. Can tell. I did great. So I did one class. So I have something here.
I don't need to be like. No, it's like. It's time.
Oh, yeah.
Don't use puzzle. Yeah, no. If you want. Oh, so you're not.
You killed a rock.
It has to be less than.
That's crazy. If you were sure about yourself, that's basically you can actually.
Yeah, I was about to sure that I actually
Smell. It's like
Does it not sound like? This. Boundaries. Your needs.
Hello, hello, hello. Hello. Hi. Thank you guys for being so patient. We are about to begin. Let me put this in full screen.
Oh my God.
Thank you. Okay. So we're going to start with combinatorics. The lecture that I'm about to give pretty closely mirrors the lectures that Anka's given and that's found in the textbook. So don't feel the need to like write everything down that I say. And also we're going to post the slides afterward. So really don't feel the need to do that. Okay, so for combinatorics, this is where we're going to have our counting rules and our balls and bins, inclusion, exclusion. Some general tips for each of the counting rules, have a specific example in mind. So something really easy. I'm going to give you a bunch of like really, really stupid, simple examples that you can just use to think of. Because if you list the counting rule that you're using, then you have the potential to get partial credit. So if you apply it incorrectly, but you know what you're supposed to be doing, then you get partial credit. Simplifying your final answer is kind of a tricky thing. So you shouldn't be simplifying things that are going to take like non-trivial amounts of time. But you shouldn't give us, like, for example, 5 choose 1. 5 choose 1 is just 5. So be a little, elaborate a little bit and simplify really simple things. And show your work mathematically and briefly explain your logic to get there. So for example, on the last homework, there were a ton of questions that were asking, like, how many ways can you count this set? How many ways can you count this set, without whipped cream, for example? And some people just put numbers down. If you're correct, then you're super lucky. If you're incorrect, then we have no idea where those numbers came from. And if the question specifically asks for justification, then you'll lose points for not providing any. Okay, so we're just going to jump right into the multiplication rule. This is my favorite rule. It comes up all the time. Remember that these rules are going to be used in combination with each other, but I'm going to lecture about them in isolation. So the multiplication rule, you can count a set S by breaking down choices into multiple steps where each step is independent from the others. So my choice at step 1 doesn't affect how many choices I have at step 2, doesn't affect how many choices I have at step 3, etc. So a problem that uses the multiplication rule might look like this. There are n choices for step 1, n choices for step 2, step 3, step 4, n choices for step 5. So in total, there's n times n times n times n times n to the 5th choices for the entire set. So let's do a really stupid example. The number of distinct ice cream cones with 3 toppings. So here we have cherries, sprinkles, and chocolate chips. They kind of don't even look that appetizing, but I promise they're supposed to be chocolate chips. So for each of the 3 toppings, there are 2 choices. There's a choice to include it on the cone or to exclude it on the cone. So I've tried to show that with the yes, no, yes, no. So we can view it as 3 distinct steps. So step 1, we're dealing with our cherries. There are 2 choices. Step 2, we're dealing with our sprinkles. There are 2 choices. And step 3, we're dealing with our chocolate chips. 2 choices again. So now I'm going to have a little participation. Because of the way that we just talked about this, how many possible ways are there to choose these ice cream cones? Give me a 1 if you think it's 1. Give me a 2 if you think it's 2. Okay, awesome. Seeing some pretty unanimous ones. But you'd be surprised. People mess this kind of stuff up. So it's always helpful to write out what your expression actually means. So 2 times 2 times 2, 2 to 3, not 3 to the 2. So 8 distinct ice cream cones. This is the example that I like to think of. It's slightly more complicated and it kind of captures a little more nuance. So how many distinct license plates can you have of length 7, where the first 3 are going to be letters and the last 4 are going to be numbers? So steps 1, 2, 3 have 26 choices each, 1 for each letter of the alphabet. And steps 4 through 7 have 10 choices each, so 0 through 9. So again, how many possibilities do we have? 26 to the 3 times 10 to the 4, or 3 to the 2 times, 6 to the, that should be 3 to the 26. Just imagine both of those are in the exponent. All right, so give me a 1 or a 2. Tons of 1s, some 2s, some confused people. Yeah, you guys were right. It's 1. So each of those choices are independent. We apply the multiplication rule. That's how we get our license plates. So this is the example I have in the back of my head when I'm thinking of the multiplication rule. Another super easy example is the number of permutations. So if I was given a set with 5 things, how many ways can I arrange that set? Well, for the first thing, there are 5 choices. Now I've taken out one of those choices. For the second thing, there are 4 choices. Take out that choice. For the third, there are 3, then 2, then 1. That's where we get like 5 factorial. So here are just some general tips. This is used when previous choices don't affect future choices. And some guiding examples are those license plates, ice cream cones, or you could also think of permutations. Now, this is the addition rule. So this is when current choices do affect later choices. So the general guideline for this is to break up our possibilities into distinct cases. And then we're going to use other counting rules in those distinct cases, and then add them all up together at the end. So what it might look like, 5 distinct cases. In case 1, there are n choices. In case 5, there are n choices. And now we're going to add them all up together to get 5 to the n choices, possibilities. Here's a kind of silly example. Anka, Martha, Tooney, Clarkson, and Obama are standing in a line. If Tooney wants to stand in an odd position in the line, how many possible ways can they do this? So there are 5 positions. How many odd numbers out of those 5 do we have? We have 1, 3, and 5. So we have 3 possible cases. Case 1, Tooney stands in position 1, 2, Tooney stands in position 3, in case 3, Tooney stands in position 5. We all get the premise of this question? Okay, so the multiplication rule kind of is going to come into effect here. So for each of these, we're going to fix Tooney's position. So in case 1, the first position only has 1 choice. It's Tooney. In case 2, the third position only has 1 choice. It's Tooney. And in case 3, the 5th position only has 1 choice. And here is how I would work through the problem. So first, I would choose somebody to go in the second position. As illustrated there, I chose Obama. Next, I would choose the next person. So how many people are left? Well, there's 3 people left. I took out Tooney from the mix. I took out Obama from the mix. And now I choose the third person. I choose Anka. Cross Anka off my list. Now I only have 2 people left, Clarkson and Martha. So for the 4th position, there are only 2 choices. Now for the 5th position, I've chosen Clarkson to be on the 4th. So I've removed everybody from my list except for Martha. So Martha goes in the 5th position. There's only 1 choice for the 5th position. So what does that give us? That gives us 1 choice times 4 times 3 times 2 times 1, which is 4 factorial. So that's 24 ways to arrange Tooney at position 1. This looks like the multiplication rule. How is this the addition rule? Well, because we have those 3 cases. So we're going to add up each possibility for each of the 3 cases. So 24 plus 24 plus 24, we're going to get 72 possible ways to arrange the line with Tooney at an odd position. But there's even another way we could count this problem. This is using the subtraction rule. These are essentially the same thing. A lot of the times you're going to be using complements. This is basically like using the complement of the addition rule. So this first fact up here is just generally true about sets. If A is a subset of S, then the size of A is equal to the size of S minus S without A. So the way we can think about that in terms of the Tooney line problem would be if S was the total number of arrangements of our line, and A was the total, or the size of A was the total number of arrangements with Tooney at an odd position, then the size of S without A is the total number of arrangements with Tooney not at an odd position, which means at an even position, right? Okay, so take like 10 seconds, try to work out this problem. You should get the same answer that we got on the last slide.
Yeah.
Okay, let's go over it. So the size of S, the total number of arrangements, that's just the total number of permutations of that 5-person line. So just like we were saying before, the total number of permutations of a size of set of a set of size n is n factorial. So the size of S is going to be 5 factorial, which is 120. The size of A, that's what we're solving for. And the size of S without A is going to be all the possible ways we can arrange Tooney at an even position. So similarly to how we did it before, if we fix Tooney at position 2, that's an even position, there are 24 arrangements. If we fix Tooney at position 4, there are 24 arrangements. 24 plus 24 by the addition rule is going to give us 48. And since we said before there are 5 factorial total arrangements, we're going to have 120 minus 48, which is going to give us our 72 again. There we go. So we just solved the same problem in 2 different ways. Imagine how difficult it would be to grade if I didn't write I was using the subtraction rule or I was using the addition rule. I would have no idea what you're doing. So please try to write it. And above all, just try to explain what you're doing using your words. Here is my TLDR of the addition and subtraction rule. So this is used when current choices do affect later choices. We're going to break our possibilities up into distinct cases, calculate those separately using other rules, and then add them all together. You can also consider finding the complement of the set that you want, if that's easier to calculate, and that would be using the subtraction rule. Bijection rule. This one should be the most natural based on the last couple units we've done. So if you have 2 sets, S and T, and there's a bijection between them, that means they're of the same cardinality, right? This has been coming up in the class a bunch of times. We're using it again here. When is this useful? Well, this is useful when S is what you want to find, but T is easier to find. There are some examples on the homework that we've had that do this exact thing, and it allows you to reuse your previous calculations. So for example, from the last homework, there was a question that said, how many ways can we arrange these 3 cones so that none of them have whipped cream on them? And that was like question B or something. And then later it says, how many ways can we arrange these 3 cones such that all 3 of them have whipped cream? If we can recognize that those 2 sets are of the same size, by the bijection rule, we just like saved ourselves a calculation. We can just say they're equivalent and just explain what that bijection is. Another example using the bijection rule, this is the one that I personally think of, is the number of ways to order the set 1, 2, 3, 4, 5, such that should say 3 is to the right of 2, apologies, such that 3 is to the right of 2. Well, we can group together the 2 and the 3 to make 23. And then we can make a bijection to the set of 4 numbers, 1, 4, 23, and 5. And then we have a much easier time. We can just use the number of permutations. So we can do 4 factorial. Do these 2 examples make sense? Are there questions about these? This is the time to interrupt.
My main issue with using this is more so like trying to define the bijection itself, kind of like how to go about it.
Yeah, so how do you find the bijection? If you recognize that 2 sets are of the same size, that's when the bijection rule applies.
Say that like straight up, if like we notice that, we don't have to like get into like establishing like, oh, like the correspondence, blah, blah, blah.
Yeah, you don't have to prove that it's like injective and surjective, right? You can just say these 2 sets are equivalent. By the bijection rule, they have the same size. Yeah, and I think the answer key for the most recent homework will come out soon, like hopefully soon enough for you to see it before the exam, but there's a really good brief explanation for the bijective rule in there you can look at. Any other questions? Okay, division rule. This is the one that I think trips people up the most. This is the one that we see misused and abused the most, but it's really kind of simple. So if you have a set S and you have another set T, where each element in S maps to exactly K elements of T, then the size of S is equal to the size of T over K. Kind of a mouthful. Here's a very stupid example. Suppose you want to count the number of cows in a field, but you're only given the number of cow legs. There is a 4-to-1 correspondence between cow legs and cows. So if there are the size of L legs, then there are the size of L divided by 4 cows. This is like kind of like a simple way to think of it, but you'd be surprised. This logic can do some pretty complex things. Does this example help clarify, or is the division rule still confusing? So if I told you that there are 16 cow legs, how many cows would you find? 4. And you'd use the division rule. You'd say there is a 4-to-1 correspondence. This is not to erase cows that have less than 4 legs. All right, so those are all the counting rules. Kind of dense, just a quick overview of them. Next, we're going to talk about the binomial coefficient. I just pasted in the definition because I think Matt explained it best. So the binomial coefficient is the number of k combinations of a set of n elements. So the number of ways you can make a group of size k out of a group of size n. And here we have just this formula that you should commit to memory. So n choose k is n factorial over k factorial times n minus k factorial. Let's employ this together. Oopsies. Okay, you are creating the next big 5-person K-pop group. You hold auditions and 80 people show up. You want to test all their chemistry to make sure you get the optimal group. So you want to test every possible group of 5. How many groups do you have to test? Well, here I kind of just gave the answer away. You're going to do 80 choose 5. I just showed the way that you can simplify it. When the numbers are way smaller, sometimes you end up with just really small integers. So here you can see I expand out 80 factorial. I get 80 times 79 times 78 times 77 should be in there too, times 76 times 75 factorial. And then I divide that by 5 factorial times 75 factorial. I cancel out my 75 factorials, and I am just left with that 80 times 79 times 78 times 76 times 77 over 5 factorial. Yes.
You have to simplify this on the exam.
You would not have to simplify this on the exam. This is far too big.
At what point do
You can stop at 80 choose 5.
You could, yeah, but say that you're trying to use this value later and they're smaller numbers, like maybe it was like 20 choose 15, or even like 5 choose 3. You can do the same thing. So you're gonna simplify by removing some terms from that factorial. This is like a very common trick to use. Do people understand the math that's going on up here? The simplification? Okay, that's a lot of groups. Next, we're going to move on to balls and bins. These guys are kind of one of the main parts of our class and some of the most memorable things from our class. These, as far as I know, are the only ones you need to worry about. You didn't talk about Stirling numbers in class, so you don't have to worry about indistinguishable balls and distinguishable bins. And you don't have to worry about the number of surjective arrangements for distinguishable balls, distinguishable bins. So if I were you, I would remember these formulas, but you don't have to memorize them because I will explain to you now how they are all derived. So distinguishable balls, distinguishable bins are the easiest. This means we can tell the balls apart from each other, and we can tell the bins apart from each other. So let's count the number of arrangements. So for each of those n balls, we have m choices for which bin to put them into. We could conceivably put all of the balls in the same bin, right? Because we don't care if it's injective or surjective here. So we could have them all in the same bin. We could have them kind of evenly split up, or any combination in between. So for each of those n, we have m choices. So m choices for the first one, m for the second, for the third, all the way up to the nth. That gives us m to the power of n arrangements. This is using the multiplication rule. Now the number of injective arrangements. So before we start reading what's on the slide up there, let's think about what injectivity means. That means if we have 2 things in the domain, they're going to map to 2 things in the codomain. And if those 2 things are not the same, what they map to is not going to be the same. So we can think of our function as being from balls to bins, and we need to make sure that each ball maps to a distinct bin. So that means there's at most 1 ball per bin. Why might this not work if n is greater than m?
By the pigeonhole principle, you put too many balls to fit into the bins, you have to put 2 in them.
Exactly, yeah. So we need to map all of our balls because that's totality. That's a principle of being a well-defined function. But just like this person said, by the pigeonhole principle, there are too many of them. We're going to have to put some additional ones in each bin. So here's how we get to that formula. We're going to go to the first ball first. We choose which of the M balls to place it into, or sorry, M bins to place it into. Then for the next ball, we choose which of the remaining M-1 bins to place it into. We took out that one bin that we already placed something in because this is injective. And we keep going until we deplete all of the bins. This is going to give us that M factorial coefficient. And then for each of those balls, there are M choose N choices. So in total, this is going to give us N factorial times M choose N. Do you think on an exam you could come up with this formula if you forgot it? Seeing some yeses and some nos. Try to commit the logic of this into memory. In the textbook, there's also a pretty good explanation that if this one doesn't jive with you, you can read that and try to connect with it. Oh, the top one is wrong, sorry. So yeah, thank you for catching that. That should be N factorial coefficient, because we might have more bins than we have balls, because this isn't necessarily surjective, right? So which one are we going to deplete first? We're going to deplete the number of bins first. So it should be N. All right. Now we're going to do indistinguishable balls into distinguishable bins. So this is where we're going to use our stars and stripes argument. So distinguishable bins means I can tell apart one bin from the next. Indistinguishable balls means I can't tell the balls apart. So I can't tell the stars apart. This means if I have one arrangement that has, 3 balls in one bin, and then a different arrangement that has 3 different balls in one bin, I'm going to consider those equal. So stars and stripes, sometimes also called stars and bars, is a way to think about this. It uses the bijection rule because we're going to kind of abstract this problem into a different problem. And the problem that we're going to abstract it to is the number of ways we can place stripes among a certain amount of stars and stripes. So if you think of the stars and the stripes as a string, that string is going to have size n plus m minus 1. So I'm going to write it on the board just to make it clear. Okay, I'm going to write it over here because I don't have an eraser. So there are n stars and there are m minus 1 stripes, because there's going to be a stripe after every bin's over except for the last one. So say we are trying to do 5 stars in 3 bins. So that would be 5 stars. And 3 bins, except we're not going to put a boundary on the last bin. So we're going to take this one away. So we're going to get m minus 1 bars or stripes, however you want to think about it. So this whole string is going to be of size n plus m minus 1, where these are the n pieces and this is the m minus 1 pieces. And what we're trying to decide is how many ways we can place these 2 stripes. So how many ways can we choose 2 places out of all of these? So I want to choose 2 places for the stripes. So maybe I choose to have 3 in the first bin and 2 in the second bin and 0 in the third bin. Well, I've just placed these 2 stripes in my arrangement of n plus m minus 1 characters in this string. So how many possible ways could I have done that? Well, just using our binomial coefficient, that's n plus m minus 1, choose m minus 1. Another way to think of it in this example, that's 7, choose 2. So we're choosing out of the 7 possible places to put the stripes, 2 of them. This is also equivalent to doing n plus m minus 1, just choose n. Does anyone have an idea of why those 2 might be equivalent? Yeah, exactly. So if you choose a place to put the stripes, you're also choosing a place to put the stars, right? So I chose these 2 places to put the stripes. That's equivalent to choosing these 5 places to put the stars. So in my kind of denominator of my binomial coefficient, this could also just be n. Okay, this one might be the most confusing, but the most used. So if you have questions about this, please ask them now. So could be n plus m minus 1, choose m minus 1. Or it could be n plus m minus 1, choose n. So choosing the number of, or choosing the places for the stripes is the same thing as choosing the places for the stars. Any other questions? Okay. Okay, and now we're gonna do the number of injective arrangements. So if it's injective, we're gonna use that same kind of function before from the balls to the bins. We want 1 ball in n of the m bins. So because there are n balls, there might not necessarily be the same amount of balls as bins. So we might have some empty bins, but we want to make sure that at least one of them, or for each bin that has a ball, there is only 1 ball in that bin. There is not 2, there's not 3, either 0 or 1. This is very simple. This is just n choose m. Why? Because we don't care which ball we're choosing because they're indistinguishable. So we're just going to choose m out of n.
Why is it n choose m and not m choose n?
So there's going to be either the same amount of balls as bins, or there's going to be less balls than there are bins. Just because if there were more, then 2 balls would be in the same bin, right? So we're going to choose a subset of the bins, n of them, that are each going to get 1 ball. So out of m of those bins, we have our subset of n. And then we're going to place each ball in like 1 ball per bin of those n bins.
N bits out of
M could be bigger than n. Yeah. So m here is going to be the number of bins that we have. There could be more bins than there are balls. Ooh. Okay. The overleaf document has not updated. There's like a bunch of typos. That's what I was doing right at the beginning of this. This is m choose n. We're choosing those. Yeah, sorry to scare people. So just to explain it again, we have m bins. Only n of them are going to get filled. So we're going to choose n of those m bins to put those balls into. And just like this person said, there might be more bins than there are balls because we're not guaranteed to have this be surjective, right? Okay, great. Thank you for catching my mistakes. Sorry about that. My overleaf document is updated. Okay, so now we're going to do a combinatorial proof. This is what we had on the board earlier. So if you get a combinatorial proof, the most important thing is don't freak out. It will be okay. It's really kind of a simple algorithm you can use to think of how are you going to prove this. So we have a left-hand side that we want to prove is equal to the right-hand side. We first are going to pick which side looks simpler. So I think the right side looks simpler. I don't know if people agree with me. Yeah, the right side looks simpler to me. So now I'm gonna try to come up with a set that I can use the right-hand side to count. So we think back to what the binomial coefficient means, n choose k. That means we're gonna choose k things out of n. So here, we're choosing k things out of n plus k plus 1 things. So you should come up with a set that has n plus k plus 1 things in it and try to choose k of them. So that is the logic I would use if I was presented with this problem, how to kind of work through it. We have the right-hand side being easier, as I just said, and we just came up with this set that we could count in a slightly easier way. So we can use the hint. Imagine that you have n plus 1 red balls and k blue balls that you're trying to place in a line. Let's come up with a set using these n plus 1 balls and k balls. Does anyone have an idea of a set that we can count using the right-hand side with these balls? All distinct lines you can make with the red and blue balls. So we have n plus k plus 1 balls. That's the same thing as saying n plus 1 balls plus k balls, right? And now we're trying to choose a line of size k. So, I'll come back to that. Yay. So here's our claim. Here's the set that we're trying to make. Both sides count the number of ways to order n plus 1 indistinguishable red balls and k indistinguishable blue balls. So now that we've come up with a way to, oh, yeah.
Like stars. Like one of them's a stripe star.
So you could use stars and stripes. It might make the argument maybe slightly less friendly. If you can come up with a simple way to do it, the simple way is always going to be the best. So n choose k, if I see that, I'm immediately going to think, how many ways out of n things can I choose k things? But if you were given, for example, like you were on the last homework, just straight up the formula, one of these formulas, for example, then totally use stars and stripes, because that's exactly what this is counting, right? Okay, so now we're gonna use what we know about our set to count it with the right-hand side. So there are n plus k plus 1 spots, and we select k of the spots to place the blue balls and the rest the red. So there are n plus k plus 1, choose k ways to order the red and blue balls. So this is using the same kind of principle here, that if we're choosing k, those are the k blue balls. That's equivalent to choosing the n plus 1 red balls. So once we fix where those blues are going to go, the red ones have to go where the blue ones weren't. So we're ordering one, ordering the other. So that's our right-hand side. Before this started, we gave you this problem and asked you to count it. Did anyone come up with like something similar to this, or did we come up with different ideas for the right-hand side? Okay, raise your hand if you have something similar to this. Okay, most people, nice. All right, so now we're gonna try to count the left-hand side. This is where we're gonna use our counting rules and where we're gonna try to explain ourselves the best we can. So using our words and using math, citing the different rules that we employ. So take like 30 seconds, try to work out a way to count the left-hand side. And notice that we have a J, so we're gonna have to define a new variable here. Okay, I'm gonna cut it off. There's a lot of chatter. Don't be discouraged if this is really hard. This is a previous year's homework problem, so they had a lot more time to do it. And this is harder than something you could expect to see on the prelim. Okay, to count the left-hand side. So here is the kind of solution that we are given. Again, this is gonna be posted, so don't worry about taking pictures. You can if you want. So here, we're gonna partition the set of possible orderings by the number of blue balls at the beginning of the ordering. So suppose there are exactly B blue balls at the beginning of the ordering, then the sequence must begin with exactly B blue balls followed by 1 red ball, or else there'd be what, B plus 1 blue balls. There are J equals K minus B blue balls remaining. Does that make sense so far? Are we following up to that point? So we pick how many blue balls we're going to start with. So maybe the first amount of blue balls we have before a red ball. And then we're going to have the total number minus those blue that we just picked left. So we then have that 0 or J that is greater than or equal to 0, less than or equal to K. Because if it was 0, how many balls would we have? Then we'd only have B balls. And if it was greater than K, then we'd have more than K balls, which we know we don't have. So after the first red ball, there are also N red balls remaining. Why? Because we started with N plus 1 red balls, right? So we take away 1, now we have N left. Thus, among the N plus J spots that are left, we must choose J of them to have blue balls. So for a fixed J, there are N plus J, choose J ways to order the remaining blue and red balls afterward. So here we're taking the total number of permutations and we're breaking them up into distinct cases. This is using the addition rule. So just like before with Toonie and line, we said, what if Toonie's in spot 1? What if Toonie's in spot 3? What if Toonie's in spot 5? Here we're saying maybe what if there's only 1 blue ball and then a red? Now what if there's 2 blue balls and then a red? Now 3 and then a red, 4 and then a red. All of those are counted in our total already. So the sum of all of them is going to get us to our total, right? They're all distinct. So when we sum over all possible J, that's where we get that left-hand side from. Ways to order the blue and red balls. Okay, so if you're given a combinatorial proof on your prelim and you have no idea how to start, you're going to have an N, you're going to have a K, probably. Pick things for those to represent. If it mimics a formula that you already know, then you can think of something that you've already seen. So think of kindergarteners and candy, or ways to order ice cream cones, things from previous discussions, things from previous homeworks. If you're given something totally random that you've never seen before, think back to your binomial coefficient. So what does N choose K mean? Well, if I know what N choose K means, I can say a set that's of size N plus K plus 1 choose K. It just means the same thing. Okay, cool. Again, this is harder than something you're going to see on the prelim. Do you have any questions about how this proof came about, ways to go about it, things like that, how to get partial credit?
Why we have B blue balls and then 1 red ball. So that's going to form that partition, right? Because you can't have, say, any other like between 1 blue ball and 1 blue ball. Because 2 blue balls, 1 red ball. There's no overlap.
Yeah, there's no overlap. So what this person asked was, are there overlaps between the cases that we're adding up? So of all the permutations, some of them are going to start with 1 blue. Some of them are going to start with 2. Some of them are going to start with 3, 4. All of those are distinct from each other. You can't start with both 1 ball, 1 blue, and 2 blue. That doesn't make sense, right?
Wait, maybe I'm just missing something, but I thought in the original setup there were N plus 1 balls, so fixing the first spot as a blue ball, there would still be N plus 1 red balls, not N.
So when we choose the number of blue balls that are going to be at the beginning, we're also choosing the fact that there's a red ball that comes right after. Because if we had, if we said there were 2 blue balls at the beginning and then another blue ball next to it, then we would have three. We'd have three blue balls.
So it also subtracts one from the red one.
So exactly, it subtracts one from the red one. That's why I go from n+1 to just n. Any other questions about this? This will definitely be on the prelim, right? Combinatorial proofs. Okay, if not, we can move on to probability.
The corrected version is gonna be posted, so don't worry. You won't have nightmares about anything and.
Actually thinking about the ways like.
You can also use the mic.
How does this work? I've never seen.
Oh, do I just
You can clip it onto your device.
like this? Is this working? I'm gonna assume it's working. Okay. In terms of like reasoning about the problems, probability ends up being somewhat similar to combinatorics in the sense of like you can format like what you're actually reasoning about in terms of like what sort of things, like what sort of outcomes you expect to work out a certain way. You just have to also match that against like the total number of outcomes, and then that fraction ends up being your probability. You will still have to justify your answers with both math and words, like writing out like your like expression of like multiplying or dividing or adding whatever probabilities to get something else, and then explaining words like how you actually got there. It's also easy. It can also be easier to think about if you were to draw like Venn diagrams or probability trees, in the sense of like it could help you see like which possible outcomes you need to consider in order to evaluate something. Oh, it's just this.
Yeah.
Okay. Okay. Probability spaces. I'm sure you guys have seen this 1,000 times before, so I'm not going to spend too much time on this particular one. A probability space contains a sample space of all the possible outcomes. So like literally everything that can possibly happen when you're running some kind of experiment. Maybe you're flipping a bunch of coins and you're looking at the outcomes. Maybe you're drawing a hand from a deck of cards, something like that. All the possible hands, all the possible sequences of coin flips. That's your sample space. The set of events F which they can fulfill. This is like this is a subset of the sample space such that like you have some subset which contains a bunch of outcomes, and all of those, like any of those outcomes represent this event happening. And you have a probability function PR that says how likely these events are to occur. So you put the probability function and it takes in an event and it returns a number between 0 and 1. And then that gives you a percent with how likely this is going to happen given like whatever sample space you're working with. Yes.
That's but like slower.
All of it or?
Yeah.
Okay. I'm sorry. Okay. A probability space. You have a sample space. It's every possible outcome that you can produce for whatever experiment you're working with. If you're flipping a bunch of coins, you might have that represent like a bunch of possible sequences that you can have for the coins. If you're working with like drawing cards from a deck of cards, you might look at all the possible hands that you can draw, stuff like that. That's all your sample space. The set of events F which they can fulfill, that's like one event is a subset of the sample space such that you have a bunch of these outcomes, and if any of these outcomes happen, then this event has happened. If you're flipping a coin, if you're flipping a coin and you're looking at the event that coin flip is a heads, then the event would just contain the outcome where it comes out as a heads, for instance. And then a probability function that says how likely these events are to occur. That's like, it takes in an event and it spits out like the percentage of the time which you expect this event to occur. If you're looking at the same event of flipping one coin and getting heads, that's 50% because like we're assuming it's a fair coin. So the probability function would output that. For complementary events, these are things where like you have two events and one of them or the other one is going to happen in any particular outcome. It doesn't really matter which one so much as both of them are not happening at the same time. And for any possible outcome that you have, one of them is happening. For instance, if we use the same example of flipping a coin, either it's going to be heads or it's going to be tails. These two are complement events because either one happens or the other. You can't have both happen at the same time because you can't have both sides up at the same time. And you can't have neither happen because you need one of the sides to be up. That's kind of how flipping a coin works. But these qualities are referred to as mutual exclusion and exhaustion, but like I don't think that's actually like those specific words might come up.
Yeah.
Hold on.
All right, does anyone have any questions so far, or do we want to try an example? No? Great. So we have an example up here, strawberry picking. So Clarence here bought a box of 36 strawberries, but unfortunately 2 of them are rotten. And now Robin wants to pick out 5 strawberries at random. So what's the probability that Robin will be having at least 1 rotten strawberry among the 5? We will be giving you 5 minutes to work on it, and then we will work through it together. Okay, great. You know where the water bottle is?
If you go back towards.
So do we have to do like a G thing? Do we have to do like a choose? Do the probabilities?
Over there, you see.
Now we don't care about
Oh, yeah, no, yeah, there's. Is there 5 events? Well, no, you should be doing 5 straw. Oh, yeah, each strawberry is like of the 5. Yeah, you're right. But we're picking 5 at a time.
It's just like, give it
We have the normal, like, we have the 5 here. Five and just quickly sort out. In there. Depending on. Or into like. It'd be like. Strawberry. That like that. Yeah, exactly. Exactly. And
All right, everyone, can everyone hear me? All right, so let's get back to the question. Usually, like, as Clem said earlier, like probability most of the time is just exactly like counting problems, in the sense that usually if you want to compute a probability of an event A, what you would want to do is that you would count the number of occurrence of event A, and you would divide by the number of events in the sample space, right? So in this question, what will be our sample space and what is the events that we are counting? Can anyone help me answer this question? Any volunteer? Oh, in this like counting, in this probability problems, what is our sample space and what is the events that we are trying to count? Yes.
Sample space is all of like, so like, it's like R is one, like all possibilities.
Uh-huh.
Well, not all, it's all the possibilities to have like 5 of the arrangements. Like.
Yeah, so the sample space here is all the possibilities of like, like having like 5 strawberries picked out of this box, right? And what is the events that we are like counting here? Can someone help me? Yes.
So in our case, since it says at least 1 rotten strawberry, what we did was we did the probability you pick no rotten.
Yeah, it's really great. Thank you. So that's like this next point that I was gonna get to. But so the sample space here is like all the possibility to choose 5 strawberries out of 36. And the event is all the possibility where Robin will pick at least 1 rotten strawberry, right? But sometimes like, it is tricky to count an event like directly. So what we can do in some cases is that we're trying to find the complement of that, right? And in this case, like they were pointing out that it's much easier to count the number of events where Robin picked no rotten strawberry. And then like we subtract that out. So how do we compute the size of the sample space? Can someone help me with this? Anyone? Yes. Yes, 36 choose 5. Right? And what about the size of the event?
Choose 5 minus 34 choose 5.
Yes, thank you. So 36 choose 5 minus 34 choose 5, right? Because you have 36 choose 5 ways in total to choose 5 strawberries. And out of them, like there will be like 34, like, you know, like non-rotten strawberries, right? So there will be like 34 choose 5 ways to choose like strawberries, like 5 strawberries that are non-rotten. And then you will subtract them. So the final answer would be 11 over 42. We are doing great, y'all. Does anyone have any question for this problem? Oh, yes.
How about you could only use that if it's like a uniform probability space?
Um,
So like each
uh-huh.
is like equally likely.
Mm-hmm.
I don't know if it is in this case.
We are like, I guess like in the sense like we are considering like, you know, like all 36 strawberries should be kind of like distinct. And then like we are saying that, oh, we are sampling 5 out of those 36, right? So if in that sense, like every permutation has like equal probability for you to be chosen. So that's why we can assume that they are like uniform distribution here. Does it answer your question?
On the test, will it be more clear like what's distinguishable and like not distinguishable?
I think that in this situation, it's just like think that they are distinguishable can help us like, you know, like compute the probability a little bit easier. It is fine if you think that they are indistinguishable in this case. It will just like change the computation a little bit. Yeah. Any, yes. You can keep it in this form over here. You don't have to like obtain the number 11 over 42 because I don't think you can calculate that in the exam with a calculator. Yeah. Any more question? If not, let's go back to Clarence.
Honestly, I might just carry this. I think it's just easier. I don't feel like putting it back on again. All right. So for conditioning and independence, conditioning is like getting more it involves getting more information about like how we like the likelihood we expect for A, given that we already have B happening. And the way we can format this is by taking their intersection and dividing it by the probability of B. This takes all the events where like all the outcomes where B happens, and it picks out the ones where A also happens, and that gives you P probability of A given that B happens. We can also use this definition to define when 2 events are independent, which is when like 2 events, like if one happens and the other one doesn't have an effect on it. So like if A and B are independent, then if B happens, then we expect the exact same probability for A. So we expect like probability of A given B is equal to probability of A. And I believe this should also say that the probability of B given A is equal to the probability of B. Forgot to put it on. That's my bad. And then equivalently, we can also say that like the probability of A intersects B is equal to like multiplying the individual probabilities. I believe this is, I don't remember if this is used for Bayes' rule or defined by Bayes' rule.
No, it's just like the definition of independent.
Yeah, okay. So, all right. Any questions about this slide? No? Cool. This is
Perfect.
Oh.
Yeah.
Okay. Then let's go straight to example. We have Toonie thoroughly shuffling a standard deck of 52 playing cards. So they're in a completely random order. There's no rigging for the like the house, the casino, or anything. This is completely random. And he's gonna draw, and they're gonna draw a card from the top of the deck. And we're gonna look at whether or not that card is drawn as a red card and whether or not it's also drawn as a king card. Do we expect these two events to be independent? Or like what sort of things, like intuitively before we actually like look at the like equation?
He wouldn't matter what suit or color. Because each suit and color has the chance of
You're saying it doesn't affect the,
Yeah, I mean, I'm saying that they should be independent because
okay,
you have like, whether you choose black or when you get a red or a black at the start, like there are 2 points in both the red and the black.
okay. Then I'm gonna give you guys like 2 minutes to reason about the problem, figure out like what you think the answer is, and then we'll reconvene. No, I was asking.
like if you draw. There's something. Yeah, but I feel like then it wouldn't be a matter of the party. And that would be a problem where like you're just decreasing the possibility more so than like your probability. So.
It's rather hard that it also, I don't know.
But I.
Yeah, I got
I can probably do it. Maybe I can just.
probability is better.
I can probably.
Are
Right,
conditions that equals the probability of R. That would show.
R and A, like R is
So we prove it one direction, we don't have to. You know what I mean? Like if we prove R, condition A, you don't have to go.
If you look here, it's
I'll play more poker, bro, instead of studying. I never played. That's scary. Yeah.
the definition of because if you move to the B, right, the left hand side will become R. But if you B times B is A and B. So, like I think like it was
All right, guys, let's reconvene. All right. So refreshing again from the previous slide. In order to have R and K independent, we have to have that like the probability of their intersection is the same as the individual probabilities multiplied together. So what do we so if we count the right side of the equation first, what do we expect the probability of R to be? The probability that a particular card drawn as a red card. Yes. Yeah, just 1/2. And the probability that that card drawn as a king.
2 over 56. 2 over 56.
2 over 50. 2 over 26. Because there's yeah 2 over 26. Because there's 4 cards in or 4 kings in a standard 52 deck. So that ends being 4 over 52 simplifies to 2 over 26 or 1 over 13. So multiplying those together ends up giving us 1 over 26. Yeah. If we counted the number of like red kings in the deck, we would end up getting 2 red kings in the deck. That's how many there are in a standard 52 deck. And that ends up giving us 1 over 26 as well. And I believe that's what it says on the next slide. Yeah. Okay. So both sides of the equation end up evaluating to the same thing. We have R and K independent. Any questions about this example? No? We can also apply this independence definition to like a set of multiple events. We can either have them be pairwise independent if we could take any 2 events in this list of events and prove that they are independent for like any 2 events that we select. Or we can show that they are mutually independent if we show that any intersection of any number of these events can be represented as the multiplication of their like individual probabilities. And you would have to prove it for every intersection if you wanted to prove mutual independence, not just the one that I put on the slide. Questions about this? Bayes rule. This is something that we somewhat started to look at on a previous slide, in the sense of like this definition somewhat comes from that. We can use like the probability of one event given the other to flip it and look at the reverse probability. And we can also look at the law of total probability, which says that like if we have some sample space that we're working with and we can partition it into a bunch of like sequence of events A1 through AN, then we can take the probability of a particular event B and look at it individually in the context of each of those A events, and then add up all of those probabilities, and those will give us the probability of B. Questions about what I just said? Good. We can also use this sort of thing for Bayesian inference. I believe this was touched on for like 2 slides in the lecture. I don't remember if there was much time to do much, but it's basically the idea that we have a particular event that we're observing, and we have some belief about like how often it's going to happen. And then we update it using new information that we learn about our situation to like redefine our probability. In this case, we're looking at the probability of A, and that new information that we're taking in is the fact that the event B happens. So now instead of looking at just the probability of A, we're now looking at it in the context of B, because we know that B is going to happen. So our new probability that we're looking at is A given B. And if you were to write this out for multiple observations, you would end up looking at this expression that I can't quite say out loud without confusing people. And then this equation at the very bottom is something that's probably going to come up decently often in those sorts of problems where you're considering Bayesian inference with multiple different new observations. So that might come in handy. Questions about this slide? Wait till I see your phone's down, so you're done taking pictures. Good.
All right, so right now we do have an example. So imagine that Victoria has 5 fair coins, Oh, okay. 2 are double-headed, 1 is double-toed, and 2 are normal, as in like, they have 1 head and 1 tail. They can only be distinguished by looking at them directly. And all the subsequent parts of this problem should be grid in sequence in the sense of like, the question in A, like the result that you have, should be considered when you work in question B, and from B, you consider that when you work in question C. So for example, the first problem is that now Victoria shut her eyes, choose a coin at random and toss it. What is the probability that the lower face of the coin is ahead? I will probably give you like 5 minutes to work on this. And then we're gonna come back again as a group. All right. Oh, question?
There's not. Oh, no, it's not.
Wait, you have 6 heads or Robbie's secretary. AC did not have AC did not meet this. That's fine. What is that? Because once you take a double dip.
We're waiting 2 more minutes. This stuff Victoria should be having. I can open it on the stuff.
It's gonna be.
Also, Victoria, have you signed up? Okay, okay. Oh, what's so fancy?
That's what we said.
Do you see anyone that's still working on it?
I can hear people. So I see
Hi, folks. Are we still working on it? Do you need like more time, or do you want me to work through it with you? Raise your hand if you need more time. Okay, a few people. Let's give us 2 more minutes. Okay. Oh,
Like in a sketchy way.
Oh, maybe not that.
Yeah. I think it'd be cool to like sit there, like something for.
Yeah, that's what we are doing tomorrow.
Yeah.
It's not us. Someone. We're gonna do it.
We're not choosing.
Wait, where am I brought stuff here, right? Where is it?
Six over eight.
It's in here. My stuff is in here.
Yeah, I know.
They has a 30.
All right, everyone, let's get back. So before we start, oh, wrong page. Okay. So before we start, I do have defined a couple of events that I think might be helpful to, get everyone on the same page. So denote that the H is the events where the coin is double-headed, the L is double tail, N is the coin is normal. LH is the lower face will be head, and UH will be the upper face is head. Does anyone have any question regarding the notation here? Not? All right. So, oh, my bad. So what is like the probability that we want to compute here? What is the event here? Can anyone help me with this? Yes. Yeah. Where's my marker? Okay. So the events that we want to compute is LH, right? And can we compute this directly, or do we have to work around somehow? Oh, yes. Oh, did you raise your hand? Oh, yeah.
Be that you pick like a double-sided coin.
Uh-huh.
And then, if you pick a double-sided coin, you know it's a 100% chance that the bottom is double-headed, and then
Uh-huh.
the probability to pick a double coin, and then you multiply that by 1/2.
Okay.
Then that would be-
Yeah. So like in a sense, like it is like a bit difficult to compute it directly, right? Without knowing like whether the coin that we are having is double-headed, normal, or like double tail, right? So we need to use something that's called law of total probability to help us with this. So we can break like like probability of like the lower coin is head, right? Is probability of the lower coin is head, given that it's double head times probability of double head plus probability of double tail, right? Plus probability of lower head given normal times probability of normal, right? We know that the probability of you pick the double head coin would be 2.5. Double tail coin would be 1.5, I believe. And the normal one is 2.5, right? For each of these, like, double head, double tail, and normal coin, you can also compute this conditional probability. So as like they said earlier, if you pick a double head, you're guaranteed to have like a head on both sides, right? So the probability should be 1 here. If you pick a double tail, you have no tail, sorry, you have no head on both sides. So this probability should be 0. And if you pick a normal coin, this probability should be 1/2 because like the coin is fair. So it's equally likely to land on, to face down on head or tail. So put all of this together, we will be able to, decompose probability of LH and give us the probability equals to 6/10. Does anyone have any question on this part? Yes.
LH given DH.
Say it again.
How do you find the probability of LH given DH?
Yeah. So if we are given that like the coin that we are choosing is double head, right? Whenever we toss it and we like, we have it like this, we know that both like the upper and the lower face must be head, right? So that's why we can compute that probability. We can reason that probability of LH given like double head would be 1 because it's always gonna be like head either side, right? Yeah, does it make sense? Yeah. Okay, great. Any more questions? Yes.
Like saying, calling it like lower is heads rather than like heads or tails. Also,
Sorry, say it again. I can't hear you.
is there a difference between having like lower head, upper head, and then, or in comparison to just doing like heads or tails?
Oh, so like how usually like a normal coin would have like a head face and a tail face, right? In this situation, the coins can also have like a case where the coin have like 2 head and the coin has 2 tails. So we use like the term upper and lower to like have like, like stay away from like the head and tail like terminology. And like the upper and lower is like analogy for like when you toss a coin, right? And then you catch it. The upper will be representing like the face that you can see, and the lower will be representing the face that you cannot see, if that makes sense. Yeah, and the reason why we compute the lower face instead of the upper, face will be relevant in subsequent part. Yeah, all right. So, oh, sorry, question? Uh-huh. I mean, like there are other ways to like compute it so that like you can get like 6/10. But if you are, I guess like, like if like you can reason and like through your equation, we can see that you're trying to use like law of total probability. You don't need to define all the events, if that makes sense. But as long as like you make it clear that you're trying to use law of total probability and you have compute each of those probability or like reason them out, then it should be full credit. You don't have to like use like formal notation like this. It's just like to help us agree on what we are saying here. Question?
We only had the bottom row of just the computation that.
You still have to explain like, what does the 1 represent, 2 and 2/5 represent, etc. Like, you can't just say like probability of LH equals to this equation. Like you will still probably get like points for calculation, but you will not get points for justification, if that makes sense. Yeah. And like, like justification, it should not be too complicated also. Like just like maybe half a sentence, 1 sentence here should be sufficient for each of them. So yeah. Any more question? Nope. Okay, let's get on to the next question. Now, she opens her eyes and see that the upper face is head. What's the probability that the lower face is head? So just to give you a bit of a head start, the probability that we are interested in computing would be like probability of LH condition on UH, right? I will give you 5 minutes to work on this and we get back as a group, okay? Parents? Oh, it's open, okay.
Yes.
I don't think they need more than, they don't need too much.
What is that?
I don't think they need too much.
They've already spent time.
Hmm?
They've already spent time with the concepts of the problem.
Yeah, yeah. I think the last one is going to be a bit tricky. Actually, there's one more like parts, but then that's like a bit tricky, so I don't add it. It's like another condition. So, um, six 24. Let's get back to 628. 627. 730. So we have a couple. Yeah.
I wish I could, bro.
No, yeah.
Wait, it makes sense, yeah, because you have all the heads with the double. Four out of the six of them.
Yeah, it's a long session, probably be a little bit tired.
Makes sense.
Just like very easy. There's a total of, you know, I'm gonna put you on
So do you?
You told him.
Oh, 5 minutes?
Yeah, because it's 25.
Like this one.
Yeah, there's only one more question after this, so
Okay, cool.
can we get to 35?
Oh, yeah, of course.
Okay, cool. All right, folks, are we ready to do this or do we need more time? All right, so does anyone have any idea how to compute this like probability? Yes.
I mean, if you know that the upper face is a head,
Uh-huh.
can't be a double-tailed coin.
Uh-huh.
So there are 4 possible coins it can be. 2 of them are double-headed, 2 of them are normal. So the probability of it being double-headed is 1/2. And if it's double-headed, the probability of the lower one being head is 1. So 1/2 times 1 is 1/2. If it's a normal coin, given that a normal coin, the top one is heads, there's a 0 probability that the bottom one is heads. So it's 1/2 times 0 plus 1/2 times 1, so the total probability should be 1/2.
It's not right. So it's a I can like work through it with you later, but does anyone have any other approach? Oh, yes. Uh-huh. Uh-huh. Mhm. Okay. Yes. Uh-huh. Thank you. Thank you so much for sharing. So you know, like oh, do you? Oh, okay. We know that like the probability that LH given UH will be the joint probability over the probability of UH, right? And this we have computed earlier is 3/5. And disjoint probability, we know that if like, like the lower head and the upper head is like, both happening, right? This means like this probability is nothing but the probability of double head, right? And because of this probability we have computed earlier is 2 out of 5. So if you divide these two, put these two together, you should have the probability equals to 2/3. Yeah, so intuitively you can also think that if you already have like the upper face is ahead, there can only be 3 possibilities. And out of those 3, only 2 of them are double-headed. So the probability would be 2 out of 3. Yes. Yeah. So if we see that, if we already know that the upper head is like, yeah, upper face is ahead, right? We know that there are only 5 coins, 5 coins, double head, normal, double tail, right? And then
2 double head and 2 normal.
oh, sorry, my bad. What is it? One double tail, 2 normal. Double tail, 2 normal. Double head. Double head. Lower face head, give it the upper face head. Okay. If you condition it, so oh, I see. I was trying to explain it intuitively, but I think my intuition was wrong. So scratch that part. Let's stick to the let's stick to the definition of condition probability. And I will try to write a clarification later on the slide, probably on like why you cannot just do it equals to 2/4. But yeah, anyone has any more questions? Yes. Say it again.
How did base rules, like how would base rules work?
Oh, base rule is like the next question. So it's not, do you mean base inference or?
I guess like for this problem, if we solved it with like base rule, like LH times probability of UH, like given LH over probability of UH. Like how would that be like wrong?
I mean like H given, I mean like if you are trying to compute like probability of LH given UH, and you say that this is equals to UH given LH times probability of LH. Oh, let's erase this.
That's 1, so they're just equal to each other. Sorry.
Probability of LH over probability of UH. I mean, like if you try to approach the problem this with this approach, how can you compute this probability? Okay, I will get to it. Okay. All right. So we are slightly running out of time, so we will just get on to the next question and work through them together. So now Victoria shuts her eyes again, picks up the coin and tosses again, right? What is the probability that the lower face will be head again? Can anyone help me? Which approach should we use for this problem? I just like answered it like 1 minute ago, if anyone remembers. Bayes rule, Bayes inference? Yeah. So we would be using Bayes inference to, approach this problem, right? So we will be interested in computing the probability that the second term, it will like the lower phase will be hit, given that we already know that the upper phase is hit last time, right? And we can decompose it a little further. We know that we can either break it down to like either double head or normal, right? And wait, let's do it here. We already know that the probability that it is double head, given that the probability that it is double head, given that the first toss is the upper phase is head, is just the same as the probability that the lower phase is head, given that the upper phase is head, right? So that's why the probability here is like 2/3. And the reason why the probability of normal given UH would be 1/3 is because we know that the probability of LH given UH plus probability of LH given normal plus probability of lower phase head given wait, when am I right? Oh, sorry. Normal. Sorry. Probability of double head given upper phase is head, normal given upper phase is head, and double tail given upper phase is head. This has to sum up to 1, right? And we know that it can't be double tail, so the probability has to be 0. And we already know that this is 2/3 already. So this must be 1/3. The other two probabilities shouldn't be hard to compute. But yeah, the final result would be 5, 6. Does anyone have any question for this one? Yes. Oh, yeah, because like we know that like the probability of like double head, normal, and double tail condition on like the upper phase is head, right? All of them plus together must be 1. And we already know that the probability of double head given upper phase is head is the same as the probability that the lower phase is head given that the upper phase is head, right? So that is 2/3. Double tail has to be 0 because the upper phase is head. So now the normal has to be 1 minus 2/3, right? So that would be 1/3. Does that answer your question? Okay. Any more question? Nope. All right. So that's it for probability. If you have any more question, please let us know on that. And I will get to you on that later. Okay, great. Thank you. Victoria. Yes.
Hi, everyone. Thanks for hanging tight. This last section is going to be on automata. I don't know Overleaf, so I made my own slides. Sorry. Is it updated? Okay, so this is just an overview. It's 30 slides for context. We're going to go over DFAs, proofs using pumping lemma, NFAs, subset construction, Thompson's construction, and Kleen's theorem. Should all be familiar. So this is like the last concluding slide you've seen in lecture on languages and automata, and I really think it sums up everything and how everything's connected. So if you're given some language and any of the three are true, you can conclude that the others are also true. So if there exists a DFA that recognizes L, you know that there also exists an NFA that recognizes that same language and that there exists a regular expression that describes L. And so you know L is a regular language. And then that last note, some languages are not regular. We can use this, we can prove this with the pumping lemma is really important. You should have your pumping lemma proofs down. So we'll start with DFAs, should be straightforward. So what you should be able to do is like just define a language for a given DFA or draw a DFA given a language. So that language should be given in English if they're asking for DFAs. And then this is our 5-tuple definition for DFA. you'll be given an alphabet. You've seen, I think, 0 or 1, A or B, maybe A, B, C. And then you have a finite set of machine states. You have some starting state, some set of final or accepting states, and then you have a deterministic transition function. So that means that every state of a valid DFA has a single outgoing arrow, a single unique transition for every letter of the alphabet. It's deterministic. So just some like tips I have is like, like understanding that script L of M is the language of M for some DFA M, and it's important to try to identify what language does your DFA recognize. It's good to find the smallest acceptable string or like word that's accepted by your language. Trace through your DFA on some sample inputs to like sanity check. And then really quickly, we're gonna do a tiny example for some DFA that accepts languages that contain the substring 1, 1. So like 2 minutes, go ahead, go.
Zero, one.
Okay, does anyone need more time? Okay, good. Should be quick enough with an example. So the way I think through it is, okay, what's the quickest way to get to a final state is just having the string 1, 1, 1. So then this is like the starting state is like 1, 1. And then if I have a 0 in this, it's like this, the same thing as like starting over. I'm still looking for that sequence of 1, 1, 1, 0. And then similarly, if we have this 1, but then we get another 0, we will go closer to our final state. And this state. And then in this final state, we can have whatever after our substring, doesn't really matter. So it's gonna be self-looped at 0, 1. So every state has 2 outgoing arrows, 1 for every letter of the alphabet for 0 or 1. Except for our final state, I just combined it. Any questions on this? If it had to start with 1, 1, 1, you might have like the hell state that you've seen in class. So just be mindful of when you need that and when you don't. Cool. So we're gonna look at pumping lemma. The textbook is really helpful for this. So L is the language recognized by a DFA with K states. So we're going to take some word from that language with its cardinality greater than or equal to K. This is going to be an arbitrary K. So we're able to compose W such that the cardinality of X, Y, these 2 strings concatenated, is less than or equal to our arbitrary K. Y must be at least 1 character, and that X, Y, Y repeated I times for any natural number I, with Z concatenated at the end, is part of the language. So everyone should have seen this before. I know this involves like concatenating substrings. Any questions on that? Okay. So for proofs using the pumping lemma, I promise it's easy, like it becomes repetitive. So it says so then in the textbook, it's very similar and they follow the same strategies. So this is just the overview of it. You need to take an arbitrary variable K. That's going to be your potential number of states for your DFA. And then you choose a string W from that is accepted in your language. So this is important because the way you need to decompose in the next step is arbitrary. So your choice of W in order to go further in your proof is really important. So with that, you make your arbitrary decomposition that follows along the pumping lemma, right? Like you want to make sure that the xy is less than k and that y is greater than 0. And then you will find along your proof by contrapositive that you're not able to hold that this last phrase, x, y to the I, z, is part of your language. So that's just the general overview. So you take arbitrary k, you pick a w, you do an arbitrary decomposition by the definition of pumping lemma, and then you use it to show that you can construct a word that's not part of the language. So we're going to look at this question from your Gradescope quiz. So this was one of the options. Steps 1 and 2 are done for you. You have your arbitrary k, it needs to be a positive natural number. And there's the w you're going to be working with. Write a proof to conclude that L cannot be recognized by a DFA with case states. So can everyone write down the w? All right, I'm gonna give you a few minutes to work on this. All right, go ahead. And really try to practice like the exact wording for proof like language, so you get full credit. My solution is only the outline, but we want to look for keywords like arbitrary, so make sure your answer includes that.
Arbitrary composition.
I threw a hint on the board with like information from the other side. You are gonna want to look at this specific case where you want y to be very nice. Please talk to people around you if you need help with your stuff. Yeah.
Like what's it, 1 and 0 to the k, like strength of y. She's taking it as y.
Sorry, that's important information. Sorry.
Answer. We have Oh, wow. So I guess we should add that somewhere, given this. It's like.
That's it, correct, so we just say, like say, that cannot be.
The way we do this is that I can't do that. Say that, I'm showing like an arbitrary. Lines. Zero. I want to make it so it can't. You should do zero.
Okay, sorry, for the sake of time, we're gonna move on. So this was my outline. So I made my W, I arbitrarily decomposed it into X, Y, and Z. And so this is how I did it. It's written in text, though, which is really ugly. So I have for my X is gonna be 0 to the n to the n. For some arbitrary natural number, it does not have to be positive. So this could be like this could be to the zeros. And then I have Y is 0 to the m, but m does need to be a positive natural number. Because we know that Y needs to at least be one character. And then Z, I just have like the rest of the string. So I have to account for however many zeros are taken out by this arbitrary decomposition. So I do, the Z is gonna be 0 to the K minus n, and then the rest of the string. That arbitrary decomposition makes sense. Yes. Because we have these variables that are not defined. These are just like general. Does that make sense? Good question.
I mean, where did the ones go?
Sorry, I was just being kind of brief. So this covers that first K. The rest of Z is this many zeros because we took out the X and Y. There's me 1, 0 to the K, 1. Sorry, that was my shorthand. Okay, so that's our arbitrary decomposition. So then if we want to use that decomposition to make this W prime, where we have Y to the second power, quote unquote, and we write it all out, that's gonna be 0 to the K plus M. So the K comes from our original W, and then the plus M comes from doing this Y twice, because we know that this is how our Y is defined. Everyone with me there? And then it's just the rest of the string. This one. Okay. This is our W prime. Based on how we did our arbitrary decomposition. And what you'll notice about this is that this does not hold the form of WW for any W in our alphabet. Therefore, we know that this is not a part of our language. By contrapositive and pumping lemma, we make our conclusion. All of the proofs are going to be like this. You make your arbitrary decomposition, and then you can usually use this one. That's what I've seen in a lot of examples. And then you find that it's not part of the language, therefore you can't. And because we chose arbitrary K is representing the space for our DFA, and that this can't hold, we can't possibly make this DFA for anything. Yes.
You're like concatenate Y.
Yeah, sorry. So that part is here. So I wrote it out this way. So we add plus M to account for this Y happening twice because we define Y.
Got it.
Yes.
Does the X need to be defined in arbitrary terms? Would it be possible only to choose X as like a certain empty string, but then define Y as like here, our K, since K is already some positive integer? Or would like X and Y need to be like 0 to the power of some arbitrary number?
And Y needs to be
So
0.
could we say X is the empty string and then Y is 0 to the power of K?
So that would not be an arbitrary decomposition. That'd be very specifically making X in our decomposition because it's string.
Just a second, like different substrates.
Definitely try to get one more practice of this. They have in the textbook as well. But I'm gonna move on for the sake of time. So NFAs, the big difference between an NFA and a DFA is you have the outgoing arrows. For the DFA must cover all the characters of the alphabet. For the NFA, that is not the case. You can have 0, 1, or more arrows. So if we're looking at this little example here, let's say this Q prime is final. So that would accept AA. Even though technically you could just keep it in this non-final state, you can also make it into having it go into the final state. So therefore AA would be accepted, just to clarify. So when in doubt, if there is some path into a final state for an NFA, and there's some path that's not into the final state, go with it being final. So NFA really ties into the next topics I'm going to go over, but you should be comfortable given a language in English, right? Drawing out a DFA, given a DFA, being able to build a given an NFA, be able to build a DFA, given a regular expression, being able to make an NFA, and then the other direction. So if you were given an NFA, you should be able to write a regular expression. And then just generally being able to define a language if you're given some NFA, just have an idea of what's going on. Yes.
Even a regular expression.
Yes.
They with generic terms like a start node and a finish node, just a big arrow with regular expression levels.
That wouldn't be an NFA. That would be like a general NFA, if that makes sense. I don't think that's a good question. I think maybe because of that like not clear part, you won't be asked that. But you're more likely going to be asked to define a regular expression given an NFA. That's a good question. So we're gonna get into subset construction. So we know that any language that can be recognized by a DFA must also be recognized by an NFA. So to go from an NFA to a DFA, we're gonna start with the states of your DFA. And we're gonna realize, okay, when we're building our NFA, our states need to be subsets of the states from our NFA. We're gonna start at an initial state where it's just the set of our initial state for our DFA. I'm gonna pop up this example. But everyone write this down. Also great. If you don't want to hear me yap on about subset construction, you could go ahead and try to get it on your own. I have the answers up on the next slide. We're just going to get started on it, but I'll walk through how to do it as well. Okay. Everyone has this down. Feel free to just go on your own with subset construction, but I'll walk through it as well. So we're gonna be referring to our NFA to construct our DFA. Bye. And we're gonna start at our initial state that is its own subset, right? We're gonna make an outgoing arrow for every letter of the alphabet. We're gonna look at our NFA and be like, okay, what possible states could I quote unquote end up in? What are our destination states? So for A, if we're looking at making our arrow for 0, we could end up in A, or we could end up in B. So then when we make our arrow here, we're gonna make the state A, B. And we're gonna point with 0 like that. Does that make sense? We're gonna do the same thing for one. We see one can only really go to A, so that's just gonna be a self. Everyone follows? Okay. So then, when we're looking at a state like this, we're gonna union our quote unquote possible states. To make either a new one or to point into an existing state. In this case, we're gonna need to make these. So we're looking at A. Where can we go? If we have a 0, we could go to A or B. And then for B, if we have 0, we can go into C. So we're gonna make A, comma, B, comma, C. That's gonna be for 0. And then to do for 1, again, we want to look at what are our possible destination states for each state within this subset. And then either create a state or make a new one. Or create a state or point into an existing. So for 1, if A goes to 1, if it would go into A. For B, it would also go into C. So then we would make A, C. This would be 1. This one's well defined. We need to make sure these are well defined. That means they have 2 outgoing arrows for 0 or 1. So that's just the general process over and over again. And then the last thing is any DFA, this is the last bullet, any DFA state containing a final state in our NFA will be made a final state in the DFA. So here we have D as our final state. So when we're done, we've drawn everything out. Any of our subsets containing D is a final state. Definitely helps to go through this a few times to really make sure you have most of it. For the sake of time, I'm gonna move on. The original problem and the answer will be posted with these slides. Sorry. We're gonna move on to Thompson's construction. So Thompson's construction refers to regular expressions. Make sure you're familiar with regular expressions. So this example has concatenation, union, and clean star. Understand how those work. And a regular expression is any language that is represented by a regular expression. In other words, regular languages are those that can be constructed from the simplest languages. So the empty set as the language, the empty word being the only character or only word accepted by your language, or just a single character. And it uses finitely many concatenations, unions, or a clean star. That makes sense. So regular expression is just a way to show a regular language. Regular languages are actually also being demonstrated by NFAs or DFAs. So just quick practice. For this alphabet, write a regular expression for these examples. I'll give you like 2 minutes on the clock. Go ahead. Turn and talk to the people around.
Frustrating. So couldn't we do like an arbitrary? No, it's not necessarily what it's going to start out. It's not too. A plus B. No.
Building structures, right? And construction that.
So this way. I think also too, mindful of the fact that we think this.
There are W's, and that's part of the question, it's like to be should start with, you W to prove that this cannot be demonstrated as a DFA. So there are W's where you do this arbitrary decomposition or even specific composition, and it holds up for the likelihood, like you just need to show that for some W. Answered your question. It's like a bit, it's a concept,
Wait,
proof like
yeah.
composite board. So we're saying this is true, let's take this down.
All the expressions you have.
Right, other than this properties of the.
Yeah, you're right.
After that, it should be simply what's arbitrary, that you don't have to somehow prove that it's.
No, it was made of it.
Okay.
And like by definition,
Followed by-
pumping like it's to ensure. that there's still a secret.
Like this, so it's really sad.
Oh, that yours is.
Slides. Definitely really been much, you know, this for the first one, like that. It's just been crazy. I don't know if that exists. So.
If it's equivalent, but there's definitely some clearance. We'll go over it now. It's a good question.
No.
No, because
You can do CAP.
Okay. So these are the solutions we had. Just like as a preface, if your answer does not look exactly like this, that's okay. It could still be equivalent. And if it is equivalent, we will check when we're grading and we'll give you credit where credit is due. These are the most simple ways to do it. Some intuitions for that first one, it definitely needed the substring AB, so make sure your AB was there, right? For the next one, we needed to guarantee that AB would never be next to each other, so we constructed using union and clean star and concatenation such that that never occurs. Yeah. Sure. For the second one, if you wanted to end the word with a C, like an added condition.
By definition, if number does not contain substring ABC, then CBC should be within the language, right?
CBC should be. Yes, and it is. So depending on how you use that clean star, so this is a 0, you do C, and then you do again, because it's a union, you do B, and then again, because it's a union, you pick C. Does that make sense? Yes.
Like the thought process behind creating the second one.
Yeah, sure. So, any A that is made must immediately be followed by the C within this first part. And then if there is a B, you could have some A after it, as long as there's no B after it, or an A, or like a C, but as you could tell from that example, this part kind of covers that. So, I would just be mindful of, ensuring certain concatenations, are impossible. So that like the concatenating of A and B is impossible based on how we construct the chains. I will have to move on for the sake of time. I'm so sorry. Okay. So for Thompson's construction, this was in your homework 7 and it's in the textbook. Also, again, for the sake of time, I'm sorry, we can't go through an example. This is how to convert from a regular expression to an NFA. So you proved that it's possible to even make this connection in class. And those are the skills that you'll want to use if you're ever given a regular expression and told to make it into an NFA. It was not done explicitly in lecture, but those are the skills that you need to use. And it's fair game for your exam. I'm sorry, we're running short on time. I would highly recommend reviewing. It was in your homework 7. It is in the textbook. And bottom line is Automata recognize every regular language. Every regular language can be expressed as a regular expression. So this back and forth is possible. So Kleen's theorem. This is the process from an NFA to a regular expression. So this I do have an example for, and it's going to be more like step by step. So there are 3 steps. You're going to merge the final states. You're going to eliminate the intermediate states, and then you're going to write your final regular expression. So what does it mean to merge your final states? You're going to be given an NFA. you're gonna create a new state F that's going to be made as your only, not including the state, the starting state, that will be the final state, sure. And then you wanna note any transitions between your existing NFA that go into a final state, brought into your new state, and then make everything except for the initial state non-final, and then make the final state final. And then we're gonna eliminate the in-between states using regular expressions, so concatenating union and clean star. We're gonna go through some examples of that. So this one sums it up really nicely. So you have a loop here, that's gonna be clean star here. You have this concatenation where it's like you could go from here to here to here, happening in this regular expression. And then you have this alternative way to get to that state as well. That's going to be union, this regular expression. And so also this first phrase encapsulates if you just went from here to here, because that clean star could also be a 0. And I want you also to notice that this first phrase kind of looks similar to our pumping lemma decomposition, our X and our Y star and our Z. And then by definition of regular expressions, you can concatenate or union or clean star with another regular expression. So that's what's happening here. This kind of sums up like visually, like if you're looking at an NFA, you have no idea where to start. This is a pattern you can do. Any questions? And you'll want to eliminate these in-between states until you have 2 left, at most. You might end up with just 1 left. And we don't want to lose the information when we're eliminating states, so you definitely want to know exactly what you're doing on this arc. Does that make sense? I know, I'm sorry, it's kind of tricky without an example right in front of you. Last step is writing our final regular expression. So these are the possible cases you'll get. I'm pretty sure you've only seen cases 2 and 4. So case 1, I doubt you'll be given an NFA that doesn't accept anything, but this is what it would look like. You'd be doing your clean 0 procedure and end up with this. And then case 3, which kind of goes hand in hand with case 4. Either way, if you have 2 states and it looks similar enough, but not quite, like you're missing an arrow, you can add like the empty word and then simplify your regular expression from there. But these are the cases, they're also in your textbook. Try to get to this as before you write your regular expression. I do have an example. I'm pretty sure this is the last example. I know we're running short on time. So we're gonna work with this NFA and try to write a regular expression for it. Let's give like 5 minutes. Go ahead.
Except so when it goes to the middle.
Oh, 0 is what I would do.
2. This transition, could we just start and then just move? One is off. Like one note. It's like
So good at
it's like I think that's what they really said. This work is showing 0 story.
This is your.
Okay, let's so like possibility 1. Just ends. Yeah, just ends. And if it doesn't happen, if you get a 0. It's supposed to follow the 1 has to follow the 0 in order to get to state P.
No, I'm
And it can also just end there. That makes sense to me. But if it goes to 0, it goes back to the star. It's like it rejects it. We need to get rid of the looping sequence combination. So it's like,
Deal with this error. It's going back.
we need to get rid of the A.
Yeah, so-
Get our numbers one.
Like a new final place, like instead of I get rid of A.
No, so within this first step, you wanna keep the NFA at that F. And just even use F as the final state, but you don't always need to do this until that step is done. Because then you get to.
Two states, it's one state. Zero.
Like, unless you.
So I don't get rid of these transitions.
Not yet. You
So
add the
I
F.
just add new trans.
All right, I'm gonna talk through as you work through it. So I wrote our NFA. I put our final state. And then I'm going to put transitions going to F based on what transitions are going into final state here. So we have this 0 transition from S into final state, so it's gonna be here. We have a 1 from B going into a final state, so that's gonna be here.
Oh.
We have it, 1 coming from S into a final state, so it's gonna be 0, 1 there. And then we have from a final state into a final state of 0, it's from A, so I'm gonna go. And then you make these non-final. That's the first step. I see some hands. Yeah. Okay.
Could you explain why you had a transition from S to F for 0?
From S to F. Oh, because I wrote it wrong. Sorry. This is. That looked right. My bad.
Actually. Like these are, these are the simplifications.
Yeah.
No, we're just.
Oh my God. We're good.
Two final six. These are not final. This is the only final.
Sorry, everyone. We wrote that one.
So it's into like the regular fashion. I see what you.
All right, so then we're gonna try to eliminate some states. I'm gonna eliminate A because I can concatenate 1 and 0 and just make that one arrow. Erase. Wait, I think I missed one. Yeah, I think I missed one. Sorry about that.
Just goes like that. This is worse. Let's get to B. It's the end.
And then here.
We're gonna get to B. Stick an end on. Like take on it. Wait, result. Not it just goes back to the initial. Oh, it's it should be 1 0 1 0 star.
So sorry, to round out that, removing the one, or just, sorry, removing A. So I made the loop from S to A to B, where it's just concatenating, and then there was a one from S to A to F. And so I added that to this existing F to F as one of the options, one of the ways to get there, yeah.
So we also choose now to remove the self loop on S and just make the transition to be 1 star 1 0.
1 star, 1 0.
And remove the self loop on S. Is that valid?
Yes, make sure you do that for every outgoing error. I would also even recommend keeping the self loop, because that is similar to one of our cases and holding on to it. Because you might get redundant phrases. Yeah.
Did you have one from S to L?
From S to F?
Or like transition from A to I?
Yeah. So there was the A. So I took this path and added it as an alternate way to get that. Sorry, I didn't do that. Does anyone have any ideas for how to remove B? Yeah.
Add 1 0. Well, 0 0. And then add 1 0 1 from S to F, and then convert the self loop the remainder half to S.
So the self loop on S is just one.
But if you go to S.
S to B to S? Yeah, so let's look at this path. We're gonna go S to B, back to S to add to this existing self loop. That's what you're saying, great. We're gonna do the 1 0. We have this one here, so that's gonna be 1 0 1 star. And we have a 0 coming back. So what we'll do here. 4 1 0 star 0. And then we just need to manage this case to F. So that's gonna be S to B to F. That's 1 0 with self loop, 1 star. Concatenated with 1. 1. Now we can remove B. And then we have 2 paths to F, so we can move those together. So that would just be. And then if you notice, we have one of our base cases. We have base case 2, because we have F as our final accepting state and S as not an accepting state. And so from there, we want to use R equals this phrase, clean star. This phrase. And that's our final regular expression. Anyone have any questions on that?
Oh, I see.
These will also be posted. Yes, they will be posted, sorry. But yeah, that was everything automata related as time permits. I hope you can see how these all connect. There are 5 minutes at the end for questions, but thank you everyone for staying and for coming. Really appreciate it. Oh, one more thing, sorry.
We have this form. Oh gosh, I'm sorry to be.
That's my.
Shoot, yeah. Okay. If you guys can fill out this form, if you love this, if you hated this, if you have feedback, whatever. This, especially if you went to the last one, did you like this one more or less? Like things like that, we'd appreciate. Happy Passover for everybody celebrating Passover and good luck on your prelim.
Yeah. Good luck. Oh, yes. Let me.